Most great when your wife calls you. No.
All right, go. Have fun.
Yep. All right. Morning, everybody. So I am her louder, ruder, nastier half. I met you guys once when I had to cover her class. So you guys were learning about earthquakes, right? So the last slide that you guys saw was, if this stupid thing wants to work, this one, right? Where you guys used this yesterday? Yep. Is everybody cool with this? Yep. Understand it? Okay, the wedge method, wedgie method, whatever they want to call it, right? And you saw this one, right? So whenever you're doing these things, I know she said she threw this up right at the end of the class. No, we never saw it. I know? Okay, so cool. All right, so when you use that wedge method, you can figure out how far away from one of these stations, from the station that recorded the little wavy thing, how far away that earthquake was. The problem is you're talking about a spherical Earth. So when you figure out distance, it could be distance up, it could be distance down, it could be distance to the left, it could be distance to the right. So what you basically do is you figure out a radius. Problem is that radius can go in any of the 360 degrees. So all you've basically figured out is that the earthquake, for example, if you look at the green dot, Nagpur in India, right? All you figured out is that the earthquake happened 3,400 kilometers away from that green dot. Anywhere on this green circle. Does that tell you where it is? No. It tells you how far away it is, but it doesn't tell you where it is. Right? So what you need to do is you need to use another station that's a separate distance away. So for example, if we look, we have Paris over here. Right? When we do the wedge method and all that stuff and you stick it in, we find out that the earthquake was 8,200 kilometers away. So you could draw a circle that had a radius of 8,200 kilometers, yes? Now, if you notice, you see that the green circle and the orange circle touch in two places. So what that's telling you is that the earthquake is in one of those two spots. So you can't use two areas, you actually have to use three. You have to use three different stations. Okay, you have to use the green station that's Nagpur, right? Which makes the green circle. You'd use the orange station, which is Paris. And then you'd use this blue station called Darwin, do the same thing, and you get a circle. And those three circles, if you did the wedge method right and everything, should all touch at only one spot. That spot where they touch is where the earthquake happened. We call that triangulation because you're using 3 points. Okay? So in triangulation, you use 3 seismic stations. You figure out the distance from each one. Okay, so in triangulation, you use 3 different stations. Okay? You find the distance from each one to the epicenter. You draw a circle that has that radius. On a map, of course. You can't just randomly draw a circle on a piece of paper. You have to use an actual map. Okay? And the point on the map where the 3 circles from the 3 stations touch, which is the little red star that you see right there, that would be the location of your epicenter. Yeah. Go ahead. Make sense? Okay, so that's how, if there's an earthquake in China, we can have a seismic station in New York, which we actually have one. It's located up in Columbia University has one. Hofstra University has one. The Museum of Natural History in the city has one. Brooklyn College has one. I think Queens College has one. They used to. I don't know if they still do. You can ask them. You find out. Okay, USGS has them all over the place. Okay, and you can use these things to identify an earthquake on the other side of the world. Even if it happens on the ocean floor or it happens at the top of Mount Everest, you can still figure it out. Cool? Any questions? Oh, you used the clicky click? I usually just hit it.
It doesn't work.
Okay, you guys did that already? Okay, so we figured out how far the earthquake is. Now we want to figure out how strong the earthquake is. Okay? So when we talk about earthquakes, we use the term intensity. Okay, because it makes scientists feel smarter to use the word intensity instead of saying how strong it is. But that's what it means. How strong is the shaking? Okay? We want to know how much the ground was shaking underneath your feet at a specific location. Okay? Now, obviously, the amount of energy that you're talking about coming out of the earthquake is going to affect this, and obviously how long it's shaking for. A quick little burst, you'll shake once and you'll be fine. If it lasts for 3.5 minutes, that's not going to be fun. Okay? Now, there's a couple of different scales we use. Okay? We have, first one, and the one that scientists use today, okay, is what we call the modified Mercalli scale. Okay? And this one works really, really well because you look at the damage that's done. Okay? So you look at what's going on in the area. Now, this is going to be affected by a whole bunch of different things. How well built an area is the area built to survive earthquakes? Is the area not built to survive earthquakes? What's the soil underneath your feet? Is there a lot of water in it? And things like that. Okay? So it's a scale that looks like this. This is actually a diagram that was on a Regents question a few years ago. Okay? And you had to look at the scale, and then they would ask you, well, what did you think the people were experiencing? Okay? It has the weird Roman numerals, but you guys have done Roman numerals how many times since like 3rd grade, so you can understand the basic concept. Right? It goes from 1 to 12. Okay? And basically what you look at is you would read a paragraph. The way this might be on a Regents or a test or something like that is they give you a paragraph describing what happened in a particular area. And based on what the people say they saw or the damage that was done, you'd have to pick one of these points. Okay? So if you look at it, it's relatively easy. If you have an intensity of a 1, almost no one's going to feel it. Okay? An intensity of 1 is less than you feel if a large truck drove outside of your house. You know, like a dump truck or an 18-wheeler drives outside your house, the windows shake a little bit. That's less. A 1 is less than that, I should say. The truck is more than a 1. Okay? A 2, okay? Some people start to feel it, especially if you're inside and you're higher up. The higher up you go in the building, the more the building's going to shake. Okay? A 3, you're going to feel it inside. You're going to noticeably feel a little bit of rocking. Okay? You might start to see things on the wall, like if you have necklaces or things hanging off the wall, dream catchers and stuff like that. They might bounce against the wall a little bit. Not bad. Okay? A 4, almost everybody's going to feel it. If you're outside, you'll start to feel the ground shaking underneath your feet. Okay? People might pop out of bed. A 5, everybody feels it. This is when windows start to crack, dishes start to fall out of cabinets and things like that. This is what you start to see in movies, right? Whenever you see an earthquake in a movie, it's always the dishes are falling out of the cupboards and everybody's running and screaming, glasses shattering. Okay? A 6, people run outside like lunatics, which is the worst thing that you can do during an earthquake. Okay? Really bad earthquake will cause windows to shatter. When windows shatter, especially in high-rise buildings, those pieces of glass turn into shrapnel that will kill you as they fall out of the sky. Okay? Running outside, not the best of ideas. Okay? When in doubt, you go to a doorway. Doorways are the most securely built structures in houses. If you stand in the doorway, the house may collapse around you. Doorways will be the last thing to collapse.
Yeah, write that down. You need to know what to do in case of an earthquake.
Okay? You always go to a doorway, you stand in the doorway, you brace yourself on either side. Even if the house starts to come down on top of you and the doorway slightly breaks, it will still hold itself up better than the rest of the house. Okay, we're at an 8, which is a VII, right? You start to get cracks in buildings, chimneys start to fall, statues fall over, okay? Antennas on tops of buildings might fall off. VII, 3 guys. Oh, 8. Okay, you get to 9, which is IX, okay? You start to get cracks in the ground. Okay, you might start to get steam, gas. This is when you're going to get like electrical fires and stuff like that, because you have gas lines running through the ground, you have electrical lines going through the ground, and you snap both of those, spark plus natural gas, fire. Okay? You get to a 10, just about every building is knocked down except for the most well-built earthquake-proof ones. Okay? Train tracks will start to bend. So you remember Ms. G taught you guys about the different types of waves? Okay? What you'll actually see is the train tracks have a wavy appearance, like railroad tracks, like Long Island Railroad subway line, stuff like that. They would bend following the wave. That's how strong it would be. Okay? You start to get landslides. Okay? The ground shakes so much that water starts to spill out of rivers, lakes, ponds, stuff like that. Start to get minor little flooding around those things. Okay, you get to 11, bridges start to fall. And I mean big bridges, like the Brooklyn Bridge, the Triborough Bridge would fall into the water. Okay, you'll start to get holes in the ground, 6, 10 feet across. And when you see those movies where people fall into the ground during earthquakes, that's what you would get from these guys. Okay, and the 12. If you ever see a 12 or ever experience a 12 and survive, you need to go see Jesus, because like you were blessed. Okay? When you get to a 12, the ground looks like water. Okay? The waves that you'd see at the ocean, you'd see on the ground in front of you. Okay? The land literally lifts and falls. It looks like little hills and valleys. Okay? Pray you never see it, and if you do see it and survive, thank whatever deity it is you believe in. Okay? Those are bad. Okay? Now, if we look at how earthquakes are scattered around the United States, where would we expect to find most of them? You get some in Hawaii because of volcanoes.
The coastline?
Okay?
On the coastline?
The coastline. Which coast?
The west coast.
West Coast, right? So the West Coast gets most of your earthquakes, right? San Andreas Fault, you guys learned all this stuff when you were like 3rd, 4th grade, yes? And that's what you see. All these red dots represent earthquakes. But you do get a lot of them up here in the Seattle, Oregon region. Right? Because the whole West Coast is a fault line. Okay? But you see, you get them scattered all over the place, even here in New York. Oops. Fat fingers. Okay? There's an old fault line that runs through Manhattan. Runs down through Harlem and the Bronx, cuts down into Long Island City, right at the edge of Queens, and then loops back into Brooklyn and back out towards Jersey. It's a very old fault. A couple million years old. Probably a couple 100 million years old. At that time, North America tried to split in half, and it didn't quite make it. So there's a weak spot in the plate right there, but it's very old and it's very deep. So we don't get earthquakes very often, but we do get them every once in a while in New York. Okay? The one state that doesn't get them is the one state where everything else is crazy and tries to kill them, and that's Florida. Florida has enough problems. Florida man is enough of an issue that you don't need earthquakes. Okay? You do notice that there's a weird cluster right in the middle of the United States. I gotta stop hitting this button.
No, it's the board.
What happened to the board?
It does it every day. I got it. You just keep talking.
Okay? So you notice there's this weird cluster right here above Texas, Oklahoma. We don't know why. The strongest earthquake ever recorded in the continental United States, or the lower 48, actually happened right in this area of Missouri. Okay? In 1860, I think I remember the date. It's called the New Madrid earthquake. Okay? It was a 10 or an 11 on the modified Mercalli scale. Okay? We think that there was also an old fault here, but we also think that a lot of the work that they do in this area, drilling for oil and gas and fracking and all those things, may be making it worse, which is why in the last few years we've gotten a lot more earthquakes in this area than we had ever had before. Fracking is a bad thing, very bad. Okay? If you look at the rest of the pictures, you see Hawaii down here. You have lots of earthquakes, but that makes sense. You put the volcanoes there. Wherever you have volcanoes, you tend to have earthquakes. Okay? Puerto Rico sits in right along the edges of plates down here in the Caribbean as well. And Alaska sits right on the edge of the Pacific plate, just like California if you work your way up. So it has lots of earthquakes and volcanoes. What's that? Okay? The scale that you guys are most used to seeing when you talk about earthquakes, most people have heard of this one before? The Richter scale? Yes? Okay, it's been used in television shows, it's been used in rap songs. Okay? The Richter scale is what we're used to. It's when people talk about a magnitude 1, a magnitude 2, a 3, a 4, a 5, a 6. in regular numbers. Okay? It was developed in 1935, which is not that long ago. I know for you guys it seems like a long time ago, but it's less than 100 years. So that's not that long ago in terms of science. Okay? What they basically do is they look at the earthquake wave. They look at that seismograph. And they look at the amplitude. This is a term you should remember from learning waves. How big the wave is. How tall the wave is on the graph. And they look at the tallest wave and they figure out, okay, this is how much energy that wave had. It's okay. It was the first real scale that we used. Okay? But it's not perfect. Okay? 1, 2, 3, 4, 5, 6. You're fine. It's good. But when you start getting to earthquakes that are really, really strong, 8s, 9s, and eventually 10s, which we've never had, it gets a little weird. And the reason it gets a little weird is that the energy is so much that so much energy is released, it's very difficult to tell the difference between like a 9.2 and a 9.3, even though they can be dramatically different. Yeah? And so if we look here, okay, here we have a bunch of different earthquakes that have happened. You actually have one that happened here on Long Island in 1884. Been a while. Okay?
Could you go back for like 2 more seconds?
No. Okay. Okay? And so, what scientists did is they kind of took the Richter scale and they kind of took the modified Mercalli scale. They put them together. And they came up with what we call the moment of magnitude scale. Okay? The moment of magnitude, which is what you see, this one up here on the left-hand side, which is magnitude. Okay? And what this one measures is it measures how much energy was given off when the earth was shaking. How much kinetic energy. You guys remember learning that? Movement energy. Okay? And so this chart is actually really good.
What's up? What do you need?
I just kind of have a question. What's the difference between intensity and magnitude?
Magnitude is just, when you use the word magnitude, it's just a number value. Intensity, when we're talking about the degree of shaking, magnitude is just a number value. So when we talk about the moment of magnitude, what we're actually talking about is the amount of energy that's released.
Thank you.
Okay? So if you look at this chart, it has the moment of magnitude, the number of values that we use. Once again, it goes from 1 to 10. Right? And then on this side, on the right-hand side, it basically tells you this many kilograms of dynamite going off is equal to that number on the scale. Okay? So if you look down here, okay, if you take about 56 kilograms of dynamite, it's about 100 pounds of dynamite. That's equal to a 2 on the scale. Okay? So most of you are somewhere between, more than 100 pounds. So about your body weight of dynamite going off is a 2 on this scale. Okay? About the amount of energy that's inside of like a little bit more than inside a lightning bolt, the amount of kinetic energy that's in there. Okay? We get those all the time. As you work your way up, if you look here, here we have all these earthquakes that happen in the United States. Okay? The strongest earthquake that we ever had is actually not on this scale. Okay? It had, the second one is, the strongest earthquakes we ever had happened in Chile, right on the west coast of South America. Okay? We had a 9.5 and a 9.7. Okay? Those earthquakes were so strong that they made the Earth's axis shift a little bit. Okay? It shook the Earth so much we actually lost time. Okay? So what basically happened is the Earth shook so wildly that it jerked forward. So the Earth usually spins, and how long does it take? 24 hours, right? So what basically happened is the earthquake was so strong it pushed it forward a little bit. Now, we lost a couple of milliseconds, which doesn't sound like a lot. But think about how strong an earthquake has to be to move the entire Earth forward. Like your song skips when you're listening to it. It skips forward a second when you're listening to it. Effectively, that's what the earthquake did to the Earth. It skipped it forward in time. Now, amazingly, it didn't kill a lot of people. And the reason why is the people in Chile have been experiencing earthquakes for their entire existence. So they build their buildings the right way. There was some loss of life, but it wasn't bad. They put the money into building the buildings right and all those sorts of things. Okay? The strongest one, like we said, we ever had here was in New Madrid, 1812. That was the year. Okay? That's the strongest one we've ever had in the United States. The lower 48, the strongest one we've ever had in the entire United States was in Alaska in 1964 on Easter Sunday. Okay? So you see it shake. Earthquake. Okay? So that's the one we were just talking about. Okay? So if you want to write down that stuff in case you didn't get it as I was saying it. Lost track of time. That means nothing. Okay. Okay. So for example, if we look at that earthquake I was telling you about, the Alaska earthquake in 1964, on the Richter scale, it only measured at 8.4 when we looked at the weight. But when we put in the amount of damage that was done, and when we measured exactly how far the two plates slid past each other and all these other things, it went up to a 9.2 on the moment of magnitude scale. Okay? The big one, the one that happened in San Francisco in 1906, was an 8.3 on the Richter scale, which means if you just looked at these two numbers, you'd say they were almost exactly the same. But when we look at it on the moment of magnitude, it actually goes down to 7.9. So if you're studying this, if you're looking at this as a geologist or a seismologist, it obviously gives you the idea of which one is stronger. Does that make sense? So, like I said, Richter scale is good to kind of like, if we're going to explain it to somebody on the news, if you're watching the news and they talk about an earthquake, they're going to talk about the Richter scale. Because it's easy for people to understand. Everybody grew up with it in school. Your parents know it. You know it. Your little brothers and sisters will learn it in school. And they say, oh, it was an 8.4, it was an 9.6. And people are like, oh, okay, cool. Now, the one thing about these earthquakes and all of these scales, they're not written in, or they're not calculated the way you normally count numbers. So if I told you how many times bigger is a 4 than a 2, what would you say? Twice as big. Yes? On the Richter scale, it doesn't work that way. Okay? The Richter scale, the moment of magnitude scale, okay? The Mercalli scale, well, not so much the Mercalli, but the moment of magnitude and the Richter scale are what we call logarithmic scales. You guys learned logs in math yet?
Not yet.
Not yet?
No, that's not.
Okay. So logarithmic scale, you're talking about exponents, right? So if you said 10 to the third and 10 to the sixth, right? 10 to the third is 1,000. What's 10 to the sixth? That's a million, right? 6 zeros. Yes? Would you say that a million is only twice as big as 1,000? No, right? It's 10,000 times bigger. Yes? Yes? Okay, so the numbers on the Richter scale and the moment of magnitude scale are like exponents. So if you have an earthquake that's a 3, and then another earthquake that's a 6, it's not twice as big. Okay? Does that make sense? It's the difference in the exponent, so just subtract one exponent from another. You'll do that same scale next year when you do something called the pH scale in chemistry. Okay? It goes 1 to 12, right? 14. Right? A 2 and a 4 are not twice as big or half as small. It's 10 to the second times 10 to the 4th. Like that. Does that make sense? Yes? Okay, earthquakes measure the same basic way. We use exponents a ton in actual real science. All right. What do we care about? When we look at earthquakes, we want to see what do they do? How do they create damage? Okay? Well, earthquake waves cause damage by how strong they shake. Okay? How long they shake, and what the ground is underneath them while they shake. This is normally the point in the year where I'd ask one kid to come up here and I'd shake the living crap out of him, but we're not allowed to touch you anymore. Okay? But obviously, if you were standing here and I grabbed you by the shoulders and I just gave you a little shake like that, you'd rock back and forth and you'd be fine. Right? Now, if I kept shaking you like this, not hard, but for a long period of time, you'd eventually get dizzy and woozy. Yes? So I don't have to shake you hard, but if I shake you for a long period of time, it'll make you dizzy. On the other hand, let's say you just stood up here and I went like, I just shook you really fast, really hard. Even for a second, you'd get all dizzy and woozy in a moment like that. If I kept doing that, you'd probably throw up on me. Then I'd get fired. Right? Does that make sense? Now, so that takes the intensity, how hard I shake you, versus how long I shake you. Right? If the shaking is strong, it's going to cause a lot of damage. If the shaking is taking a long period of time, it's going to cause a lot of damage. If it's both, it's going to cause a buttload of damage. Buttload being a scientific term. Okay? Now, the third thing, geologic profile of the land. What the hell does that mean? Okay? Imagine you were standing here and you were wearing a pair of big, heavy boots. Right? Good boots, good quality, and I started to shake you. Right? You could hold on to the ground pretty well because your boots have traction. Yes? Now, imagine I put you on and you were wearing a pair of shoes that had real flat bottoms and the floor was wet. And I started to shake you. How would you move? You'd fall. You'd be sliding all over the place, right? Even if I shook you with the same amount of force both times, right? What you were standing on would be affecting how far you would slide and ultimately how hurt you got. Yes? The same thing happens with an earthquake. If you have a building that's sitting on solid ground, it's not going to shake as much because it takes a lot more energy to move those molecules back and forth. So more energy goes into the ground than goes into the building shaking. Okay? But if the building is sitting on top of sand, okay, it's going to make the vibrations that much stronger. Okay? There's a Bible quote, "Fool was a man who built his house upon sand. Smart was a man who built his house upon rock." Okay? And it's supposed to be a thing about faith, but geologists love to use it because that's what they say you should do with houses. You should build your house on rock. Because if the ground shakes, it won't shake your house as much. You build your house on sand, it's going to make your house shake all over the place. That's why if you ever buy beachfront property, you're going to pay a buttload in insurance. Plus water damage and all that other fun stuff. Okay? What your building is made of. Yes, ma'am. Okay? What your building is made of. Okay? Is going to affect it. If you build, remember the story from when you were a kid, Three Little Pigs? Yes? You build your house out of straw, what happened to the house? Knocked down. But out of bricks, what happened? Did it fall over? Same basic tenet with earthquake. If you build your building well, it's got good support structure, it's got redundant, weight management and all sorts of stuff, it'll survive. You build your house out of a piece of crap, it'll fall apart. Perfect example of this, okay, was a few years ago. Anybody in here Haitian? Haitian set? Usually I get one or two. A couple of years ago, there was a really bad earthquake.
I'm Asian.
You're Haitian. Okay. So you remember the earthquake that happened in Haiti? Do you have family down there still?
Yeah.
6 years ago, 7 years ago, I think it was. Okay. It was a really bad earthquake in Haiti. But Haiti sits on the same island as the Dominican Republic and very close to Puerto Rico. Unfortunately, the buildings in Haiti, due to all sorts of messed up reasons, are not built to the same level as they are built in Puerto Rico and the Dominican Republic. The same earthquake completely and utterly devastated Haiti, knocked down buildings, killed hundreds of people, unfortunately, because their buildings weren't built well. Whereas in other regions, for example, the earthquake in Alaska killed 6 people, and it was a 9.4. The earthquake in Haiti killed thousands. It was like a 7. Why? Because the buildings were built so poorly that they just collapsed on people. Yes?
Do you think this is cool? It's about something?
Most buildings in New York would not survive a 7. The reason is buildings in places where they know they have earthquakes have to be built to a certain standard nowadays.
Remember what I told you about engineers in California and Alaska? They have to have a separate degree because they have to know the code for earthquakes.
They're better now. Like if you go to Long Island City, all that new stuff that they built in Long Island City, all those towers, those things would be more likely to survive because Now they build things for the once in a lifetime earthquake. Back in the days, like when this building was built, probably not. Okay. Also, a lot of times what they do is they put buildings on rollers in California. There's giant wheels on the bottom, so that if you get a bad enough earthquake, the building rolls a little bit, but doesn't collapse. That's how they built it. Okay. So this was Haiti, the earthquake in Haiti. Okay. This was the earthquake in Alaska. Haiti, Alaska. Heck of a lot stronger. That building was being demolished. You can see them taking it down, which is why it wasn't really well structured, built well. So it collapsed. But the building right next door, perfect. Okay? How well you build your building, definitely a dramatic effect. Okay? You don't need to know this. This is for the honors kids. Although that can happen with earthquake. Whoa. The ground basically turns into quicksand, sucks up your car. And then after the shaking stops, it turns back into solid ground. It basically what happens is if you have really wet soil, when you shake it, the water comes up and kind of turns it like muddy. So anything sitting on top just sinks. But then once the earthquake stops, the water either rushes away or sinks back into the soil and turns into solid ground again.
How do we get them out?
Jackhammers. This is not old. This is from 2010, 14.
Yeah, I love that.
This is in New Zealand, Christchurch. Okay, landslides. I don't know why it's red. Okay, you can get this sort of stuff happening. Sinkholes. Okay, you can get that happening. Landslides, ground erosion. Okay, you can get that. Well, how much would it suck to be on that block, those two blocks, but then everybody else is fine? Right here. See your neighbor just sail by in a buffalo. Yeah. Okay. Now, once again, it depends on what you're on. Okay. So that Alaska earthquake, you had all these houses that were built on these cliffs. Okay. The soil underneath was loose, and you had a lot of sedimentary rock and a lot of water in it. When the earthquake happened, this nice little neighborhood went from looking like this to looking like this and slumping forward. You guys learned about slump and all that stuff, right? It basically slid forward. There's a house in there. You can see a wall and some stairs. And then the rest of the house is over here. Basically what happened is the land just slumped forward in big sections and slid down the side and moved about 200 meters or 600 feet forward. Okay? Fire. Remember how we talked about the pipes breaking?
Yes.
In modern civilization, once we started developing fire, even in ancient civilizations, once we use fire to light our houses, the ground shakes. What happens to the torches that are in your house?
They fall.
They fall. What were the houses made of?
Wood.
Wood. What's the furniture made out of? Lots of things that can burn. Okay? One of the big problems we have with earthquakes after the fact is usually fire. Okay? Whole sections burn. Big earthquake that happened in Japan where the nuclear reactor went to crap a few years ago. Whole sections of Japan burn. Why? Because the gas lines break and the electrical lines break. Spark plus natural gas. Big fire. The term that for some reason students always think has something to do with weather. Okay? A tsunami, Japanese word, literally means big ass wave in Japanese. Okay? It means big wave. That's what it means. Okay? The technical term is a seismic sea wave, an earthquake ocean wave. Oh, I'll stop talking.
Okay.
Okay? Basically happens with tsunamis is you either get an earthquake that happens underneath the water or really close to the edge of the water. Okay? And those vibrations get transferred into the water. Okay? So here, you see, you get an earthquake happen right there. And so you see the waves radiating out from the little red explosion marks. Okay? That energy gets to the top of the ocean and the waves spread out, like waves do when you drop a pebble in water. You get the waves just spreading out. Okay? But they move super fast. Out on the open ocean, waves can move up to 835 kilometers per hour. That's about 600 miles per hour. Okay? Now, there's lots of water underneath. So the waves aren't that big. because all that energy is spread out across the whole ocean. But the closer you get to the land, the less water there is underneath. But you still have the same amount of energy, roughly. So what happens? That energy has to go somewhere. So what does the wave do? The wave goes up. Okay? And you notice the waves get closer and closer and closer. And eventually what starts to happen is the waves start to meet, which means you had a big wave and a big wave, and they meet, so now you have a very big wave. Does that make sense? Okay? And they start to slow down, which means they start to stack up on each other even more and more and more and more. And so what happens is you get this big wave. But the weird thing is waves, what we think of a wave is only half of the wave. That's the crest. You have the other part, which is the, remember touching the teeth? Trough. Does the word sound familiar? Yes?
Yes.
The hill and the valley of a wave?
Yeah.
Crest and the trough. Okay? So what happens with a wave is when you get a tsunami coming in, what happens first is the wave pulls out, like when you're at the beach. But the wave can be a mile long. So the water will pull out a mile out to the ocean. But the thing is, it's a wave. Whatever pulls out must eventually come back in. And so it comes in and it can go a mile in or further. Most people have seen this in a restaurant at some point. The famous picture, you see it in Japanese restaurants all the time. This is an actual picture of an actual tsunami, of a wood cutting from an actual tsunami in Japan.